Hi, Mick McQuaid here on day 18 of iste780, Data-Driven Knowledge Discovery. And this is the lab on support vector machines. We're also going to be doing support vector classifiers. And before we start, I should mention that we're scheduled today to also talk about support vector machines with more than two classes. So let me just say a word about that. The textbook doesn't say too much about them. It basically says there are two approaches. We're going to actually use one of those approaches, and it's going to be completely opaque to us. Actually, R is going to handle the details of it. The two approaches are one versus one classification. That approach, simply if we have more than two classes, does a pairwise bunch of support vector machines for every pair of classes that we have. So if we have two classes, obviously we would only need one. If we have three classes, we would need three, and the number of comparisons that we need are going to be k choose 2. That's the total number of comparisons. So we do those pairwise comparisons, and then the way that we choose the classification for a particular object, for a particular observation, is we take the test observation into the class to which it was most frequently assigned in the pairwise classifications. So the other approach is to do k support vector machines, k support vector machines, where for each one we choose one dimension and compare it to one predictor and compare it to all the other predictors, one dimension and compare it to all the other dimensions. So it's as if there are two classes. The dimension being considered is one class, and all the other dimensions sort of glommed together are the other class. And here the outcome is a little bit different. If you think back to how we formulate the problem, we have this long expression beta 0k plus beta 1k times x star 1 plus beta 2k times x star 2. We take that expression comes out to be positive or negative, and we assign to one or the other class depending on whether it's positive or negative. Remember, we set that that's either if it's equal to 0, it's on the hyperplane. If it's greater than 0, it's in one class. If it's less than 0, it's in another class. But we can use the actual magnitude of that expression now. And so in this case, we assign the observation to the class for which the greatest magnitude of that expression is achieved. And the intuition for it is that that it represents the highest level of confidence that the test observation belongs to that class. So that's really all the textbook says about those two topics. There's also a short section on relationship to logistic regression. That section is marked by a steep grade symbol. So I was planning to skip it, but you might want to read it. It's not bad. It's very prejudiced against support vector machines. It uses the term marketing in talking about support vector machines, which I think is a little out there. But it shows a little bit about the similarity between support vector machines and logistic regression. I don't think it's really that difficult to comprehend. But in any event, I am skipping it. So let's get to the lab. So the lab uses this library, iste780. I forgot to turn on R here. Let me turn on R. Okay, now you'll have to download this library, and it has some dependencies. So I've downloaded this library previously, and this has got the SVM function plus another function we're going to use called tune. Okay, so we're going to set seed to 1 so we get the same results. Part of the time we're going to get the same results as the textbook. Part of the time we're not going to get the same results because there are some, well, in any event, let's just proceed. Okay, so we're going to create some example data, and we're using this, we're creating a matrix of random normal variables. There were going to be 40 of them. This expression doesn't need to be this way. This could be 40 or 10 times 4 or whatever. They're simply doing that to remind us that it's going to be 2 columns of 20. This is just a reminder. This parameter is what actually makes it be 2 columns of 20. Excuse me. So it's normally distributed with mean 0 and variance of 1. Okay, now y, we're going to have be a repetition of 10 minus 1s and 10 1s. And let's look at these two things. So we have this matrix now that's 2 columns and 20 rows of random normal variates clustered around clustered around 0, excuse me. And y is simply a vector of negative 1s and 1s. Now, is this a separable? Let me plot this before I do this. So this is going to make them closer to being separable, this expression here. So what I'm going to do is do this first. And let me drag this plot onto the display and adjust it a little bit. Okay, and you can see it's very not separable. But now I'm going to do this function here, which is going to take all the x's that correspond to a y equals 1, and I'm going to add 1 to them. And all the x's that correspond to a minus 1, I'm going to leave alone. So that's going to have the effect of making them closer to being separable. It's not going to quite do it. I know because we set seed to 1, so I already know what this is going to look like. And basically, if it weren't for that observation there, I think we would be able to do it. But that observation makes it not linearly separable. Okay, so now we make a data frame out of this. And one point that I make here in the comments is that x here is a parameter. X on the left side and y on the left side here are parameters. And we have named our variables x and y, and they appear on the right side. And R is not confused about those because the parameters can't appear on the right side, and our variable names can't appear on the left side. Okay, now let's do a linear support vector classifier. So this is not the same thing as a support vector machine. This is less flexible than a support vector machine. And the plotting library is exceedingly ugly. This is actually representing a straight line. So for some reason this plotting library isn't good enough to take advantage of the graphics adapter that I have. And so it looks quite ugly, but basically we've got a straight line here that is the separating hyperplane. And then the margin around it is designated by the x's. Now I should point out that the minus 1s are all the items that are in black. Whether they're zeros or x's doesn't matter, o's or x's doesn't matter. It's whether they're in black, they're classed as minus 1. So you can see that there's 1 here that's red. The reds are all classed as 1. So these are all correctly classified. This is the only observation that's not correctly classified, this one sitting over here. Everything else is correctly classified. It doesn't matter whether they're O's or X's in terms of classification. It's just the color that determines the classification. What the O's and X's refer to is what is a support vector and what is not. So all the X's are support vectors. So these two are support vectors. These are support vectors. This is a support vector. And so these determine the margin around the hyperplane. And the O's play no role. whatsoever. So we don't really care where the O's are as long as they stay where they are, as long as they stay away from the margin or the hyperplane. Now the indices of those x's are 1, 2, 5, 7, 14, 16, and 17. And that means that they correspond to these rows. So row 1, row 2, row 5, which are not visible here, but row 7, which is visible here, row 14, row 16, and row 17. Those are all support vectors. Oh, and there they are again. Okay, and if we summarize the SVM object, we'll see that there are these 7 support vectors, and that 4 of them correspond to -1. So the first one in the first position here corresponds to the first level listed here, and the second one corresponds to the second level here. And we can also see that graphically in this case, because there aren't very many of them. So if we just look at this graphically, we'll see that there are 4 black x's that correspond to -1, and 3 red x's, these 2 plus this one, that correspond to 1. Okay, now we're going to change the cost. So here we made the cost high. Now here we're going to make the cost, this is the C from the textbook, we're going to make the cost really low. So what do you expect is going to happen? So think about this for a second and think about what you expect to happen to this picture. So we're going to have the same picture, but with a different value of C. How will the picture look different? Okay, so I'm going to plot it now. So have firmly in your mind how it's going to look. If you haven't thought of it yet, pause the video and start it up again when you have a guess that's backed up by a reason. Okay, now if you guessed that there were going to be a lot more support vectors and the margin would be a lot wider because the cost is lower, you're correct. That's exactly what you're seeing here. So there are many more support vectors. And let's just see how many. So there are like, I don't know, I think 16 or 17, I've forgotten now, support vectors. So smaller C leads to larger margin and more support vectors. Okay, and now we cross-validate. So we should always think about cross-validating to determine what the best value of C is. And later, when we do actual support vector machines, we're going to have another parameter that we're going to want to manipulate also. Okay, so set C to 1, and now this is the cross-validation technique in the 1071 library, or iste780, whatever it's called. It's not really a very memorable name, is it? So we have to say what the function is. We have to say what it is that we're modeling, where the data is coming from, what kind of kernel. This could be either linear or polynomial or radial. And what it is that we want to test. So in this case, we're going to test the cost with these, about 7 values, 0.001, 0.01, 0.1, 5, 10, and 100. So we're doing 10-fold cross-validation on these 7 possible models. And so that's, 7 values. So if we now summarize tune.out, or tuneout, here are the 7 models. Now we want to check for which one is the best. The best one is going to be the one with the lowest error rate. And the lowest error rate is right here, 0.1. And that's the one with the cost is equal to 1e minus 0.1. So that's 0.1, which is what it says here. So it's just different notation for this same numeral here. That's where the best performance is. Error of 0.1 and cost of 0.1. Okay, now what does tune store? This tune function stores in this. Remember we created this tune out object from using the tune function. And it stores a bunch of things, and one of the things that it stores is exactly what we want, the best model. That is model number 3 here is now stored, so we can just use this as a model. So let's store it again. We could just use it like this, but the textbook likes to shorten names, so it likes to create new names. I'm of the opposite mentality. I prefer to use the most raw names possible so that I can more readily understand what's going on. But they're using the shortest names possible so they can readily understand what's going on. So it's just different attitudes. Okay, so let's look at a summary of the best model. The summary of the best model is that it has 8 support vectors on each side, 8 for -1 and 8 for 1. And it has a gamma as well. Even though this is linear, it has a gamma that we're not going to play with until we get to radial. Okay, now let's create test data. So we built the model using the training data, and now we're going to test the model with test data. So let's create test data. And we're going to use exactly the same expressions to create it, except instead of x and y, we're going to call these x test and y test. And we're going to stretch it as we did before, and we're going to create a data frame out of it as we did before. And now we're going to make a prediction using the best model on the test data. So the model created with the training data, we're going to use on the test data. And now let's see how it does. And the way it does, so this is funny. I mean, this has actually turned out differently different times that I've done it. So you may not get exactly the same result. I may or may not have put in the seed correctly or something, but generally I get this result, 19 out of 20 correct. But sometimes I get 20 out of 20 correct. So now let's try it. We're going to do exactly the same thing, except with cost equals 0.01 instead of cost equals 0.1, which is what the best model prescribed for us. Because we'd like to know whether cross-validating really made a difference. This is just for our own educational benefit. We should trust cross-validation, but just as an educational activity, we should do this, and we should get a worse result from this. So let's see if we do. Here again, I've gotten randomly different results. They've always been worse than the best model, but in this case, it's one worse, slightly worse. Okay, so now let's do a linearly separable example. So what we're going to do is now we're going to stretch further. And when we stretch further and plot, let's plot these, and we'll see that this is now just barely separable. We should be able to draw a straight line. You know, we should be able to draw a straight line between these 2 points basically without covering any of the red points. So now let's create a data frame out of that. Remember, we stretched x, that didn't actually change what's in the data frame. Now we've created a new data frame with this separable example, and we're doing the linear on it, the linear kernel on it. And a summary of this is we only have 3 support vectors. 1 for -1 and 2 for 1. Let's take a look at the result. And here again, this represents a straight line, even though it looks like a sawtooth function. It's not a sawtooth function. This is a straight line, and we can see that 2 x's lie pretty much on it, and then there's 1 x of representing -1 near it. So this is the separating hyperplane. These support vectors dictate the margin. Now let's change it. So what we just did was we did it with cost equals 100,000. Let me just make a note. And you tell me, what do you expect to have happen here? In fact, pause the video. If we lower the cost very much, think about what it is that you expect to have happen. Pause the video if you don't know. Make a guess and have a reason for that guess. And what happens is we have a lot more support vectors, and the margin got much larger. So the margin is now dictated by all of these support vectors all over the place here. This again is a straight line, represents a straight line. Okay, now finally we get to the support vector machine. So we set seed 1 again to get the same results as the textbook, although we're going to eventually deviate from the textbook here too, I think. Okay, and here we're doing the exact same thing, except that this time we have a 200 row by 2 column matrix of X, and we're pushing 100 of those points. The first 100 of those points are being pushed in the positive direction. The next 50 are being pushed in the negative direction, and the last 50 are being left alone. And Y we're making into a bunch of ones and twos. So we'll have 150 ones and 50 twos. And the 52s are going to be at the end, so they're going to be ones that weren't pushed, so they should be in the middle. And we're making a data frame out of it, and we're plotting it. And remember I said that the 52s should be in the middle, and indeed they are, more or less. I mean, these are all randomly generated numbers with a normal distribution, but we've artificially added 2 to these, and we've artificially subtracted 2 from these, and we've left these alone. Okay, now we're going to split off a training data set, and this is notation that we've used before. If the first argument to sample is an integer, then it means that we're going to draw our sample from the integers 1 to whatever this number is, so 1 to 200, and we're going to draw 100 samples. So that's going to be our training data. And so we're going to, so that's going to be a list of numbers. In fact, let's just look at it. Let me just display it here. And so you see it is random numbers from 1 to 200 without replacement. And so those are going to be our training data, and then the rest are going to be our test data. So half training data, half test data. So now we fit a support vector machine with a radial kernel to that training data. And let's plot it. And of course this looks much more interesting. So what we've got here is a nice egg-shaped region that represents those last 50 observations. And the X's are all the support vectors around it. And it looks pretty good. There are some errors, but this looks pretty good. And what's nice about this egg-shaped function is that I can imagine a natural process. I can envision a natural process that might make this happen. We're going to look in a second at something that's not so natural looking. Okay, and so here we've got 37 support vectors. Now we're going to do the same thing but with a much higher cost. So what's going to happen to the number of support vectors and the size of the margin? We have fewer support vectors now, although we still have a lot, and the margin is much narrower, and this region looks ridiculous to me. It looks like this must be the eye of a bird. This is the head of a bird. This is the bird's mouth, or maybe a turtle mouth is wide open. And this is just the front of its body here. So it's, I don't know, it's just some crazy function. This doesn't make any particular sense, and it's probably a big overfit to the training data. It's probably not that useful. And yes, we now have a very bizarre shape. Okay, so now let's cross-validate. So this time we're doing 2 things. So we have, again, SVM, Y against everything else, which is just X, X1 and X2. The training data. So we're performing the cross-validation on the training data, and then we're going to take the model that we get from that and try that out on the test data. So the kernel radial is going to make this a support vector machine rather than a support vector classifier. And now we're not just going to do C, cost. Cost is what the textbook calls C, and we're going to check on 5 values of that. We're also going to try 5 values of gamma. We're also going to cross-validate on gamma. So we're going to get the result of this should be what is the best value of C and what is the best value of gamma. And it says here that the best value of cost is 1, the best value of gamma is 2, the best performance is 0.12. So I'm going to believe that. I think the textbook gets it differently. I can't remember for sure now. Last time I did it, my results differed from the textbook. And let's just see what happens when we make a prediction. Now we're doing the prediction differently. We're doing this in a different step. Oh yeah, look, see, I've put in my what I had before, which is not what I have now. So now my correct predictions are okay. See how that arises? So that the fraction of correct predictions is 90, which is the same as the textbook. Yeah, the textbook results were 90%. When I did this before, I got 84%. So I think it's quite possible that you'll get them differently depending on where and when you, say, set seed 1. I think one thing is I've done this over and over again, and so I may have at some point lost track of where I put in the seed. Okay, now we're going to do rock curves, and unfortunately, our rock curves are going to look the opposite of the way they look, I think, in the textbook. So we're going to create. So we have to load this rocker library, and be sure that you notice that that's case sensitive. And it also has some dependencies, so be sure you get its dependencies. And then we're going to write a short function here to make rock curve plots. So this time when we do the SVM function, we're going to add a parameter to it. It says decision.values equals t. So we output these decision values, and that allows us to create the rock curve. And we're actually going to do several rock curves. Okay, so now this is the optimal values. So gamma equals 2 and cost equals 1 were the optimal values that we found. So we're going to do a rock plot like that. And now it's right side up. So maybe I messed up before. So this is the way that it should look. Previously when I did this, I got it upside down. But in any event, what we want is for it to hug the corner as much as possible. The more it hugs the corner, the tighter the fit. I think I've actually left something out that was in the textbook, so I'm going to pause here and come back. Okay, I'm back, and actually I had not okay, so this was the I think this was the last thing that I did, right? Yeah, okay. So now what I'm going to do is create a more flexible version by increasing the value of gamma by quite a bit. And I'm going to add that more flexible version to this plot. So this rock plot has the add parameter on it, and so that and the color is red. So I've just added this more flexible version. And again, this just doesn't look very good, but this curve does hug the corner more tightly than the other curve. It should be more, it should be less chunky. I'm not sure what the graphics problem is here. Okay, now what am I going to try? So we got a more flexible curve. Oh, these were on the training data, right? Okay, so notice that the data here says train. Okay, and up here also. All right, so now down here, so let me just make a note of this. I guess I should say more flexible model here. Okay, so now I'm going to try the test data. So this is everything that was not trained. And this curve, it's hard to see, but this curve is very similar to this curve. Not as good, perhaps, but pretty good, pretty close. And now we're going to do the same thing with the more flexible model, with the high degree of gamma. And here we get a much worse performance on the test data than the training data, the more flexible one. And this is intuitive. We should expect this, that the more flexible we are with the training data, the more likely we are to overfit on the training data and to be out of touch with the test data. Okay, and I think is that it? No. Oh, multiple classes. I forgot we have to do multiple classes. Let's do multiple classes. So we're going to add a third class to our existing two classes. So we're binding X, row binding X to a matrix that's just like X. And we're going to bind Y to a vector of 50 zeros. And then we're going to stretch the x's that correspond to the zeros. And what are the dimensions of X now? 250. So we now have 200, before we had 200 observations, now we have 250 observations. And we can't check the dimensions of Y because Y is a vector, but we can always check the length of a vector, and the length of this vector is 250, so it matches X. Now we'll put them both into a data frame, and we're going to reset the graphics device to be just a single graphic that will take up the whole space. And now here is a plot of X and Y. And you can see that there are now three classes, the red, the green, and the black. Now we're going to simply say that we want a radial kernel. And here's what we get. And that's it. That's all that we have to say about multiple classes, that we can do multiple classes. I can't even tell you whether this is a one-to-one or one-to-all method that R is using to achieve this. Okay, so now we have a short application here, application to gene expression data. So this is a cancer-related data set, and we have 63 rows and 2,308 columns. Okay, and the suggestion that the textbook makes so we create a data frame out of that. And the suggestion that the textbook makes is that with so many variables, a linear classifier will be very easy. So let's try the support vector classifier. And indeed, it looks like we've got 58 support vectors. And there are no errors in the training data. So we have 8 correctly classified as 1, 23 correctly classified as 2, 12 correctly classified as 3, and 20 correctly classified as 4. And these are, this is some cancer-related data set. I think I mentioned that. Okay, but that's on the training data, which is much easier to fit than the test data. So let's create a data frame out of the test data. So we have test data. This is actual, live test data, which is test data from patients. So now let's try a prediction. And what is it going to be as good? Not quite as good, but it's still really, really good. And that is, I guess, the best advertisement that you can have for support vector machines is that they do well. They provide a excellent separation between classes, and so that's what we've seen here. Not as good as the training data set, but still very good. So support vector machines are very popular, and I hope you've enjoyed doing this little lab with them. I'll look forward to talking to you tomorrow, and thank you very much for your attention.